Hello, everybody. This is my talk on ADSB and how to improve your reception of it if you've got an ADSB set up at home. My name's Chris. I'm an IT, help desk guru kind of person. I do a lot of electronics in my spare time, and that's probably my most favorite thing. I inherited a stack of radio equipment when my uncle died a few years ago, and I've just been starting to get into the radio side of things. And I also like the future of rapid prototyping. So I have a couple of little CNC machines and a 3D printer at home. So now instead of buying parts, I just make them so much quicker. So when I started trying to use a RTL SDR to receive, ADSB signals, I had a problem where, what antenna do you use? So when you get your little RTL device, you get a crappy little antenna. So I gave it a shot with that, which was absolutely terrible. I then had a look at some forums and found a whole stack of other people trying to find the perfect antenna as well. So this is a list of the antennas that I considered and some of the ones that I tested. So number one, the crappy antenna. And from that, you get about 35 kilometers of range out of it, which is reasonable, and that was pretty impressive to see any planes that were coming past. I then plugged it into my scanning antenna, which is the one on the image, and that gave me about 150 Ks on that. And then I tried a standard little dipole, just made with a terminal block and some copper wire bent, plugged into it, and that got around the same as the Discone scanning antenna got. I looked at making a ground plane antenna, but went, nah, stuff that. It would have been okay, but yeah, it was a bit of work and it'd destroy a nice connector. I then looked at lots of people saying they were having good results from the coax collinear, which is where you get a piece of coax and you cut it up in certain spacing of wavelengths, and then you connect the center conductor to the shield and the shield to the center conductor, and you stagger it, alternating along your antenna. And yeah, that was okay. That still only got about the same reception as the others, and it was also quite a big antenna, because that was about, millimeter long. I had a look at something that people were trying out called the Franklin dipole, which is a dipole that has big loops bent into it, or like right angles bent into it to somehow select the frequency down or notch it down to what you need. And then I tried the one that seemed from reports to give the best reception and to be the simplest to make. Now I'll explain the poor man's compact J-pole after this. All right, so this is the J-pole antenna. So it's very very compact. Much better. All right, so the J-pole is compact and it covers a fairly narrow frequency band. It's a 3/4 wavelength antenna, and it doesn't require a ground plane. So if you're mobile and you don't have a large piece of metal or a grounding spike, then it'll work fine. It's also the same antenna that is actually used on most of the commercial plane systems. So most of those have a J-pole antenna because they're good for transmitting and receiving. And it's very easy and fast to manufacture, and if we have time, we can actually chuck one together tonight. So all you need to make it is some wire cutters, pliers, a soldering iron, piece of scrap coax, and a ferrite core. Now, the accuracy of this antenna is based on the accuracy of manufacturing, and a millimetre at the ends of each of the antenna, the stub and the, what's that one called? The main radiator. Any slight differences from the measurements you're meant to have will offset your frequency by quite a bit. Yes?
It's not streaming your slides.
Oh.
It's streaming your audio.
All right, let's have a look. I don't even know where your window is gone anymore.
So it looks like it is?
Yeah,
okay.
It says that's
We'll keep going.
that screen's live. Maybe there's somebody watching who can give us some feedback. Try and get back to. All right, hang on. I've lost my presentation. Yep. No video? Oh, cool. It's not that?
Okay, you keep going and I'll worry about it because you're doing the right thing.
Okay. Because I can see it on this other one. It says it's...
Oh, here we go. That was
That better? I've got too many things sitting everywhere.
Whatever you did there.
Aha. All right. Still working? Can you see the video now? Cool. Excellent. All right. So when you're measuring this, you have to be fairly accurate. Now, the link I've got at the bottom of the slide is the design that I used. So there's a very good little instructional guide on how to measure all the bits and cutting it. Now, when I cut mine, it was out by a little bit, and I just filed the ends until it got better and better, and then, yeah, picked a point to stop at.
Can I ask one question?
Yep.
If it's too short,
The frequency will be way higher than what you're after.
could you just like solder to extend a little bit your reflection?
Yeah, the changes in materials sometimes cause issues, especially at higher frequencies.
Yeah.
The speed of lightning, your solder's going to be moving at the speed of lightning. Let's see. Alright, so you can't see this at home, but everything I've got all the bits that would be needed. Some old coax cable is the best to find some nice copper wire out of to make your antenna. I use the wire off the crappy antenna that comes with it for making the little bit of wire you need to connect the antenna to the SDR. Now the wire thickness that you use also affects the bandwidth. So in my one on the roof, I have 0.8 millimeter copper core out of some really thick old Foxtel cable. And the only problem is the thinner you go, the more precise you've got to be with all of your measurements, because it does affect it more, because you narrow the bandwidth that you can see. So yeah, if you start shifting the frequency off by a little bit, then you're not going to see the signal you're after. So for my antenna, because it goes on the roof and it's going to be in all the different weather conditions, it's quite easy and cheap to just chuck it in a couple of bucks worth of PVC piping with standard end caps. Now, with the bottom one, when you put the bottom cap on, you have to get your USB cable through it. I used a Coca-Cola bottle cap because they fit with a little bit of work over the end of a 20mm bit of PVC pipe. And you can easily cut it and then fill it up with some silicon sealant or some liquid electrical tape is a good one to use. So the total build cost is under $40, including your RTL SDR and all of your bits of coax, everything you need. Now, also on that mast there's a weather station and a GPS timing antenna. I have a GPS timing receiver so that I can synchronize everything if I need to.
These photos are from your roof?
Yes, that is on the roof of my house. Oh, that's the roof of the garage. Now, one of the problems I saw looking at all of the forums was that lots of people had heaps of stuff in between their antenna and their receiver. So they'd have 5 or 10 or 20 meters of coax. They'd have a low noise amplifier. They'd have some kind of filter as well, and all of the different connectors that went with all of those. So for every connector or device you chuck in line with it, you're going to have some losses. So the way I thought of to avoid this was to put the SDR in the antenna and connect it as closely as I could. The SDR, I took the connector off it and soldered the thin coax that came with the crappy antenna onto that. It then does a couple of loops through a ferrite core to balance it, and then onto the actual J-pole itself. And all of that fits inside the tube. So it's all in one piece, and then all of your data just runs down your USB cable. And I've had no problems with 5-meter USB extension cords with the Raspberry Pi. And I'll add some pictures here once we've built one. Now, the problem with enhancing your reception of ADSB is that all of the signals are on one channel, and so you get a lot of noise and you get a lot of planes transmitting over the top of each other, especially at busy times of the week when there's a lot of planes coming in and out of Melbourne. The dump 1090 software that I use on the Raspberry Pi, it has basic error correction that I think is by default on, which can fix small errors. And then it also has some other options to give you more complex error correction. Now, it does do a very good job, but it chews up a lot of CPU. And on my original Raspberry Pi 1, it was struggling once they're over 50 planes. And once I had around 300 kilometers of reception. So once I switch to the J-pole, I get over 350 kilometers of range on it. So can see just into New South Wales, just over the border, and just to the tip of Tasmania. Now, in certain directions, there's hills in the way, so it's not as good, but it's still a very good result. With the Raspberry Pi 2 or 3 or the Banana Pi, I haven't had any problems with it maxing out the CPU once there were too many planes and too many errors to correct. So the theoretical range, based on the curvature of the Earth and propagation from the transmitters, is about 450K if the planes are at 30,000 feet. Now, if you want to see how the commercial systems work, there's a link at the bottom here that is linked to the patent of one of the receivers, and that has a very nice technical description of how they recover multiple signals that are overlaid. And I was hoping to put in some images of what that looks like, but it was quite hard to find some good images of it. So for the professional units, they have FPGAs and DSPs to do all of the signal analysis, and most of them do 8 or 16 times oversampling of the signals, so they have a lot more resolution than the real signal. And then they analyze all of the different signal strengths they can see in that and split it out into separate streams, and then analyze them all as if they were the only plane that they were seeing. Now, can you do that at home? I didn't think so, but one of the other members here spotted a site that somebody had managed to program it into the FPGA on their Blade RF, and apparently you can do the hardware oversampled signal strength analysis version of it. So it'd be nice to chuck that on somebody's Blade RF here and see what happens. So with the 16 times oversampling, you can recover up to 9 overlapped signals at once, and that's how the commercial plane systems work. So at home, I also run a couple more Pis that do airband reception. Now, airband is another thing that you can check out with your SDR receiver. It has all of the voice communications from either automated ground services or ground control, air traffic control from ground to planes, or plane-to-plane communication, air-to-air communication. And there's a bit of software that runs on the Raspberry Pi called RTL SDR Airband. Now, that the bandwidth for airband is from 108 megahertz to 136 megahertz. So your standard little SDR with its 2 megahertz of bandwidth isn't going to see many channels, but you can still see a whole heap of them. And if you have a couple of spare RTL SDRs, I have one that's set to look at the air traffic control signals because most of the towers are near each other. And then I have another one watching the emergency band. And then I have the third one I just set to wherever I think there might be things. It doesn't have a scanning feature yet, but I think they're thinking about adding that in. The different sections of the frequency range have got different services in them. So all of the bottom half of it is automated services and beacons and all things important for planes, and they're transmitted at fairly high power and fairly wide bandwidth. They're nearly all 50 kilohertz wide, AM. And then the rest of the channels up high, mainly 25 kilohertz, but because of the amount of small private planes now in Europe and in America, they're setting aside some of the frequencies and dividing them into 3 smaller frequencies each. So instead of having 25 kilohertz voice channels, they have 8.33 kilohertz voice channels. So if you're ever looking in that zone and you've set it too wide, you'll hear a chance to hear multiple people at the same time. But it does make it easier to scan then, because you'll get more channels at the same time. The airband software can record MP3s, and it does voice detection. So when it picks up a voice, it'll start recording, and for any channels that you've defined for it, or you can have it stream them all over an IceCast server.
Speech to text.
Yeah. And you can even stream it to to some of the AirWatch sites, and they'll know which plane is on what frequency. And when you click on the planes, you can listen to the audio from each plane. Now, the other receiver I have is an ACARS receiver. So ACARS is SMS for aeroplanes, made in the 70s. And now that's an interesting one to watch. There's I think there's 8 channels, but most of them are only used in Europe and America. The worldwide one is the one that I tune to, 131.550 megahertz. So most of the messages are automated. So in the plane avionics systems, when the doors are all closed and the seals all go, or the landing gear's raised, or taken up or taken down, it sends out a flight phase information broadcast saying that the plane's on the runway, or the plane's taken off, or the plane's left the gate, or the plane's approaching the gate. So that because the air crews get paid different amounts for different stages of the flight, which is just crazy, because you might get delayed on the ground and they don't want to pay them the amount that they would if they're in the air working.
For safety reasons, it's more
No. So a bit crazy, and they'll send, if there's any baggage changes, a couple of minutes before takeoff, well, probably 20 minutes before takeoff, when the pilots are doing all of their weight calculations and fuel calculations, they'll send them a message saying how much cargo they've actually chucked on board, comes over your ACARS thing, or any cancellations, so that the flight crew know, the air hostesses or hosts know that certain people aren't on the plane. So they update all of that information, and you can send back simple little messages, or you can type out complex messages. Now, it is plain text, because back in the 70s, like lots of other things, they didn't think anybody'd be listening to it or have the equipment. But now everybody can have a $10 device listening to this. So there are lots of recorded messages that are quite interesting. Lots of sports results are sent from the companies to their flight crew, like Super Bowl scores, like every couple of minutes. That kind of crazy use, like things you'd use SMS for, they will just use this for. Yeah. Any kind of issues, ill passengers, anything like that, they can transmit to the ground if it's a non-emergency, so they don't have to radio. Why does that not work? So in the future, there's a few things I want to change. The RTL SDR, if you rip its USB plug off, or take the metal enclosure off the USB to make it small enough to fit in things, you will find that it does get very, very hot, because it uses the USB outer shell as the heatsink. Yeah. So the chip may overheat. So on the one I made, I got the smallest heatsink I had and machined some holes in it so it would fit over the little capacitors that are sitting around the main chip, and then stuck that onto the chip, and that works quite well. But I would like to make a proper copper foil heat spreader that will work much more effectively, because in hot days on summer, it does randomly stop working and you have to go and unplug it for 5 minutes and plug it back in, and then all of your planes magically appear. With the reception, lots of people in Europe and America, because they're seeing like up to a few thousand planes within their range, they will have sector antennas, directional antennas on their roof looking in different directions, and then run all those into one Pi to do it. And you can run multiple copies of dump 1090 and stream them into one master copy to chuck it all back together. And it'll get rid of all the duplicates for you, which is nice. So it mixes them up, so it gets the best one. So I can either do that, although I do like the idea of trying out some FPGA programming. If I can learn about that stuff in the next year or so, and and do it that way instead, and use the same antenna and everything, but recover much more of the planes. At the moment, when it's really busy, I still get a few errors popping up. And I want to make a dedicated ACARS antenna and airband antenna, because currently using my big scanning discone, it's pretty crap. It's very noisy. And if I can get a better SDR that can cover the entire airband, then I'll be able to record every single airband at once, which could be interesting. Probably take up a lot of space. And I also want to try and receive a signal called HFDL, which is the HF version of ACARS. So for when they're out of range of airport, there's lots of places in the world where you're between two continents and there's nothing. And if you have an issue out there, nobody's going to know about it. So they use HF version. There are a certain amount of stations around the world, and they all overlap each other by a little bit. So if any station goes down, they still have, it'll still work. It has redundancy. All the ones within a couple of thousand Ks of here. Yeah, but only when they send out the HFDL transmissions, which they don't always do. But apparently you can see all the flights down to Antarctica for the US base. They have to use it there because there's no other way of getting reliable messages. And it doesn't resend. It doesn't have any kind of real, like, modern error correction in it.
And it's also clear text, isn't it?
Yes, it's clear text. Yep.
Do they like ping pong back and forth every now and again? No. They might on those flights for safety. They'll probably send them check-in messages.
Is there an HFDL on this specific frequency?
There are actually a lot of frequencies. I did have notes in here, but I don't have the notes for that one. Yeah, I don't have any of my HFDL notes because I had the number of stations and I had the some of the frequencies. They're all down between 6 and 30 megahertz. Yeah. So if you've got a hammered up converter, or you've got one of the SDRs that can go down really low, then you should be able to pick those up. And there are a few bits of receiving software, but nothing that's been updated in the last 10 or 15 years. It's all from the early days of digital reception by ham radio operators. So most of it's Windows based and needs a sound card. And yeah, you use an external scanner to feed the sound in, and yeah.
It's room for a project then.
Yeah. So, but people are looking at it, doing it for the newer SDRs. So hopefully soon there's a Linux program that does it. And thank you to everybody who helped, and you guys for being here. Yeah, the Russell and Topaz and the South American pen testers who were at the drinks last Friday, who were all going to be here.
Yes, they don't
But-
like the rain.
Oh, well, it was raining last time. They sat out all night in it.
Thank you very
All right, thank you.